Imagine an evening sky that contains everything, from the glow of your local streetlight to the faint light from galaxies billions of light years away. And underneath it all, a whisper of something older still. That whisper is the cosmic microwave background, the afterglow of the early universe. It fills space with a soft, remarkably uniform glow, a bath of ancient light that is the same from one edge of the sky to the other, differing only by tiny ripples in temperature and density. Those small ripples would one day become galaxies and clusters, stars and planets, and everything we know. But the uniformity itself is a puzzle. It is as if the entire sky agreed on a temperature before there was time to speak. For decades, the Big Bang model gave us a cosmic timeline that starts hot and dense, and then cools as space expands. This picture predicted many things correctly. It explained the abundances of light elements like helium and deuterium. It anticipated the discovery of the microwave background. It gave us a framework for how matter forms structures under gravity. Yet as astronomers began to look more carefully, three deep puzzles emerged, quiet but persistent, like notes held too long at the edge of hearing. The first was the horizon problem. It asks a simple question. How did opposite sides of the observable universe come to be so similar when, according to the speed of light and the age of the cosmos, they could not have exchanged information or heat? If space began hot and then expanded, regions far apart now should never have had time to coordinate their temperatures. And yet, across the sky, the microwave background is nearly uniform to 1 part in 100,000. The universe looks like it's settled on a common recipe before it could have mixed the ingredients. The second was the flatness problem. The geometry of the universe appears almost perfectly flat in the sense of Euclidean geometry. Parallel lines stay parallel. The sum of angles in a large triangle is very close to 180 degrees. In cosmology, this flatness depends on a delicate balance between the total energy density and the expansion rate. If the initial conditions were even slightly off, the universe would curve noticeably over billions of years. Too much density would lead to a quick collapse. Too little, and space would curve like a saddle and expand too fast for structures to form. Somehow, the balance is extraordinarily precise. The question is not only why it is flat now, but how it stayed so flat for so long. The third puzzle involved relics predicted by certain particle physics ideas. In the early universe, as it cools, fields break their symmetries and release exotic particles. Some grand unified theories predicted heavy relics such as magnetic monopoles. If those theories were right, and there was no additional mechanism, the universe should be littered with these relics. Observationally, it is not. The sky is clear of them. These puzzles do not ruin the Big Bang framework. They invite a deeper layer, a gentle subtext beneath the main melody. In the late 1970s and early 1980s, several physicists began to explore that subtext. The idea they found is called cosmic inflation. It proposes that, very early in its history, the universe underwent a brief phase of extremely rapid expansion, faster than what we see today by an unimaginable factor. Not just expansion, but exponential expansion, where distances doubled and then doubled again on timescales far shorter than a heartbeat. The name inflation might suggest a balloon suddenly swelling. The analogy is not perfect, but it offers a helpful picture. Take a wrinkled rubber sheet with tiny irregularities. If you stretch it dramatically, the wrinkles become smooth, and the small hills and valleys flatten out. What was once close becomes far, and what was once small appears uniform. Inflation, if it happened, would stretch the fabric of space in a way that smooths curvature and irons out irregularities, while also pushing apart any dangerous relics to densities so low that they become effectively invisible. Within this picture, regions that now seem causally disconnected actually were once close neighbors before the Great Stretch. They had time to exchange heat and information to settle on the same temperature. Then inflation spread that uniform patch across a cosmic scale, leaving behind subtle fingerprints in the form of those tiny ripples in the microwave background. There is something almost paradoxical about a mechanism that creates structure by flattening. Inflation blurs and calms, and yet it also seeds complexity. Quantum fluctuations, the faint jitter of fields at microscopic scales, get amplified by the expansion and become the seeds of galaxies. In this way, inflation connects the very small to the very large, a quiet bridge between quantum physics and cosmology. In the next moments of our story, we will step more carefully into how inflation might have worked, who first imagined it, and what it means that the universe carries signatures of this early calm explosion. We will move slowly, like eyes adjusting to the glow of a distant lighthouse, letting the details emerge in soft focus. Because what inflation changed was not only specific predictions, it changed the kind of questions we ask about the universe and what we dare to consider as its first breathing moments. Let us now trace the first threads. We begin with a classical picture of the Big Bang and the puzzles it left on the table, and then we watch as a new idea takes shape in a graduate notebook, an idea that would make the early universe both smoother and more imaginative than anyone expected. The standard Big Bang model, without inflation, is a story of cooling and expansion. Matter forms as energy condenses into particles. Neutrons pair with protons to build light nuclei. Electrons join with nuclei to make neutral atoms. And light, once trapped by charged particles, suddenly can travel freely. That moment of release left the cosmic microwave background, which we still observe today, as a nearly uniform sea of microwaves coming from every direction. What this model struggled with was not the broad strokes, but the initial conditions. It assumed a hot origin and let gravity take the lead from there. But why were the initial conditions so special? Why so smooth? Why so flat? And why are there no leftover heavy relics from high-energy physics? The horizon problem can be felt in a kitchen. If you heat water unevenly, it takes time for the temperature to even out. You need molecules to collide and share energy. In the young universe, any such sharing could only happen at the speed of light. Yet regions near the edge of our observable universe had not had enough time to talk to each other by the moment the microwave background was released. They should not agree so precisely. Unless, of course, they once were in close contact before being pulled apart faster than their signals could keep up. The flatness problem is like balancing a pencil on its point. It can be done, but any small deviation grows quickly, and the pencil falls. In cosmology, any deviation from perfect flatness tends to grow with time as the universe evolves. For it to remain so flat today, it must have been extraordinarily flat early on. Inflation, instead, makes flatness not a delicate accident, but a natural outcome. Stretch any curvature on a surface rapidly, and over large scales, it looks flatter and flatter. Like the Earth's surface appears flat from our vantage point, though in truth it curves on a globe. Inflation amplifies our flat patch to cosmic size. The monopole problem is more technical, but the intuition is gentle. Some theories of particle physics suggest that as the universe cooled through a sequence of high-energy symmetry changes, it would produce heavy, stable particles. If they were made in abundance, it would dominate the mass of the universe today, contradicting observation. If inflation occurred after those particles formed, it would dilute their abundance by an enormous factor, spreading them so thinly across space that they would be practically impossible to find. In 1979, a young physicist named Alan Guth found himself wrestling with these puzzles. He was thinking about phase transitions in the early universe, moments when the vacuum state of a field changes, like water freezing or boiling. At high temperatures, a field might be trapped in a false vacuum, a state with higher energy that resists change. In that state, the pressure is negative. Negative pressure, in general relativity, is a source of accelerated expansion. Guth realized that if a patch of space became stuck in such a false vacuum, it would expand exponentially. This could iron out irregularities and dilute unwanted relics in a breathtakingly short time. The idea was electric. Inflation could solve the horizon, flatness, and relic problems in one stroke. But there was a catch. Guth's first version relied on a sudden change from the false vacuum to the true vacuum through bubble formation. While the inflating space grows absurdly fast, the transition happens locally. The bubbles struggle to collide and complete the transition smoothly. The result is that the universe either remains stuck inflating or ends up with a chaotic patchwork that does not resemble the uniform cosmos we observe. This became known as the graceful exit problem. The solution emerged through refinements that turned inflation from a dramatic jump to a slow, steady roll. Andrei Lind in the Soviet Union, and independently Andreas Albrecht and Paul Steinhardt, explored a version where a scalar field, often called the inflaton, rolls gradually down a gently sloping potential. As long as the field moves slowly enough, its energy density acts like a nearly constant vacuum energy with negative pressure. Space then inflates exponentially for a finite time. When the field eventually picks up speed and reaches the bottom of its potential, inflation ends gracefully, and the energy stored in the field converts into a hot bath of particles and radiation. The universe reheats, returning to something like the starting conditions of the Big Bang, but now with problems solved and seeds sown. This slow roll picture turned inflation from a sketch into a working mechanism with testable predictions. It said that the universe would be remarkably flat and uniform on large scales, but not perfectly so. There would be a specific pattern of small variations in density, produced by quantum fluctuations in the inflated field and in the geometry of space itself. These fluctuations would be stretched across cosmic distances by inflation, then re-enter the horizon later as ripples in the density of matter and radiation. They would leave a fingerprint on the microwave background and on the large-scale distribution of galaxies. It also suggested a new way to think about beginnings. The phrase Big Bang can conjure an image of an explosion into empty space. Inflation shifts the image. Space does not explode into something. It expands within itself. The energy that drives the expansion is part of the fabric. In that sense, inflation is a quiet explosion, a rapid swelling of scale without a blast, and with a physics we can analyze. The details of the inflated potential determine how long inflation lasts, how rapidly the field rolls, and how strong the fluctuations are. Cosmologists often speak of the number of E-folds, which counts how many times the scale of the universe doubles during inflation. To solve the main puzzles, we need around 50 to 60 E-folds for the patch that becomes our observable universe. That is a vast yet finite amount of stretching. From this calm stretch, a universe like ours can grow from a tiny, causally connected region. The thermal uniformity is no longer mysterious. The flatness is no longer precarious. And the dangerous relics are pushed away beyond our horizon. But a good theory asks for evidence. It makes predictions that can be checked. Inflation made several. It predicted that the universe would look flat on large scales, that the spectrum of fluctuations would be nearly scale invariant with a slight tilt, and that those fluctuations would be mostly adiabatic and Gaussian. It also predicted a gravitational wave background, a faint wash of space-time ripples produced by the same inflationary process. These predictions would take decades to test. They involved building instruments that could measure the sky with exquisite sensitivity and control of noise. They involved checking and rechecking for subtle signals in the oldest light we can see. In the next part, we will watch how those predictions met the sky. We will hear the names of satellites and experiments that listened to the microwave background with patient attention, and learn how the quiet explosion left marks that we can measure, that we can hold in plots and maps, like fingerprints from a time when the universe was a toddler, just out of its cradle. Imagine a surface of water so still that the smallest breeze leaves patterns that spread and shimmer. Inflation turned the quantum breeze into ripples that would eventually shape everything. To follow that path, it helps to consider how quantum fluctuations work. Even in empty space, fields never sit perfectly still. The uncertainty principle ensures that they jitter, borrowing energy for tiny moments and then giving it back. During inflation, space itself expands so quickly that these fluctuations are stretched beyond the scale where they can oscillate. Once stretched, they become effectively frozen, like waves moving so fast that they appear as stationary undulations. Later, as the universe expands more slowly, those frozen ripples re-enter the horizon and begin to evolve under gravity and radiation pressure. In the language of cosmology, these ripples are perturbations in curvature and in the density of matter and radiation. Their statistical properties are nearly scale invariant, which means that the amplitude of fluctuations is almost the same across a wide range of sizes, with a gentle tilt slightly favoring larger scales. Simple slow-roll inflation predicts this tilt. The numbers that describe it, called the slow-roll parameters, are directly related to the slope and curvature of the inflattened potential during inflation. These ripples show up most clearly in the cosmic microwave background. Before recombination, when the universe was about 380,000 years old, the plasma of protons, electrons, and photons behaved like a coupled fluid. Gravity tried to pull matter into overdense regions. Radiation pressure pushed back. The result was a series of acoustic oscillations, sound waves in the early universe. When atoms formed and photons decoupled, those waves stopped. The pattern at that moment is recorded in the microwave background as hot and cold spots on the sky, and the power spectrum of those spots, as a function of angular scale, shows pronounced peaks and troughs. The location and heights of these acoustic peaks encode the geometry, contents, and initial conditions of the cosmos. Inflation makes specific predictions about that pattern. It predicts a spectrum of scalar perturbations, the density ripples, that is nearly scale invariant, with a spectral index slightly less than 1. It predicts that the fluctuations are coherent, born from a common origin, so that the phases of the waves line up to create clear acoustic peaks. It predicts that the perturbations are mostly adiabatic, meaning that all components of the plasma fluctuate together, and that they are nearly Gaussian, with any deviations being small. Inflation also creates tensor perturbations, primordial gravitational waves, whose amplitude is tied to the energy scale of inflation itself. The relative strength of these tensor modes, compared to the scalar modes, is quantified by a parameter called R. Many models of inflation predict values of R that could be within observational reach, and the pattern these gravitational waves would leave is a very specific swirl in the polarization of the microwave background called B-mode polarization. Before we describe what has been seen, it is worth reflecting on the astonishing idea at the heart of this narrative. The birthplaces of galaxies began as quantum fluctuations of a field in a universe smaller than a speck. Inflation magnified them to cosmic scales. Gravity then took these tiny differences and drew matter into them over billions of years. In the end, the grand filaments of galaxies we map across the sky are the heirs of quantum chance. It is a story that softly knits the micro and the macro, without losing the calm of the telling. From a historical point of view, the first major observational milestone was achieved by the COBE satellite in 1992. COBE, short for Cosmic Background Explorer, measured the spectrum and fluctuations of the microwave background. It confirmed with great precision that the spectrum is a nearly perfect black body, which told us that the radiation truly is a relic of the early universe. It also detected the first anisotropies, the subtle variations in temperature across the sky at the level of 1 part in 100,000. This confirmed there were seeds for structure, in the right amount to grow into galaxies under gravity. In the decade that followed, ground-based and balloon experiments refined those measurements and saw the first hints of acoustic peaks. Then came WMAP, the Wilkinson Microwave Anisotropy Probe, which made a full sky map with far greater resolution and sensitivity. But WMAP measured the positions and heights of the first few acoustic peaks and found that the geometry of the universe is nearly flat. It measured the spectral index and found it slightly less than 1, consistent with inflationary predictions. It also found that the fluctuations are predominantly adiabatic and Gaussian. The baton then passed to Planck, the European Space Agency's high-precision satellite, which observed the microwave background across 9 frequency bands with exquisite control over foregrounds, such as our own galaxy's dust emission. Planck confirmed the flatness to high precision and measured the spectral index to be about 0.965, a gentle tilt that fits well with slow roll inflation. From these data, cosmologists could begin to rule out some simple inflattened potentials, like those that grow too steeply with the field value, while favoring plateau like models that produce the observed tilt and small tensor amplitude. At the same time, other observations of the large-scale structure of the universe, from galaxy surveys to measurements of baryon acoustic oscillations in the distribution of galaxies, agreed with the picture drawn by the microwave background. The initial conditions look adiabatic and coherent. The universe is nearly flat. The seeds of structure have a scale-dependent amplitude that matches slow roll expectations. The search for B-modes, the swirly polarization signature of primordial gravitational waves, is still underway. Linking device, telescopes like BICEP, Keck Array, the South Pole Telescope, Polar Bear, and experiments in the Atacama have pushed down the upper limits on R, the tensor to scalar ratio. The current bounds are tight, telling us that if inflation occurred at a very high energy scale, the gravitational wave background must be weaker than some early models predicted. Some families of potentials, such as simple power laws that rise too quickly, are now disfavored. Others, including models inspired by modifications of gravity, like the Starobinsky model, or versions where the inflatten lingers on a flat plateau, are consistent with what we see. Alongside this, there have been careful searches for non-Gaussian signatures, which would reveal interactions beyond the simplest picture. So far, the sky looks remarkably Gaussian, with any deviation small. That quiet Gaussianity is a success for the simplest inflationary models, which predict randomness with a very specific statistical fingerprint. A beautiful additional signature predicted by inflation is the presence of correlations on scales larger than the horizon at recombination. Because inflation stretched perturbations to scales beyond causal contact in the standard Big Bang picture, we should see specific alignments in the temperature and polarization patterns. Observations of the temperature polarization cross-correlation, particularly a negative correlation at large angular scales, match the inflationary expectation. It is an echo of superhorizon physics, rendered in the oldest light. This convergence of evidence has turned inflation from an intriguing idea into a leading paradigm for the early universe. It is not just that one prediction worked. It is that many independent features align. Geometry, statistics, correlations, polarization, and the distribution of galaxies all sing in harmony. Yet we should keep an open mind. Inflation is a framework with many possible implementations. The exact identity of the inflatten, the precise shape of the potential, and the detailed physics of reheating remain open questions. Different models predict different values of R, different levels of running in the spectral index, and tiny deviations from Gaussianity. The next generation of experiments aims to sharpen these measurements and perhaps glimpse the B-mode whispers of primordial gravitational waves. If detected, they would give us a direct window into the energy scale of inflation, a glimpse into physics at energies far beyond what our accelerators can reach. Before we look ahead to those future tests, we will pause and step back, using analogies to ground these ideas until they feel as familiar as a walk along a quiet shore. When we return, we will see how these equations tell a story of smoothing and seeding, of a universe tuned by expansion to become a home for structure, and of a deeper humility about our place in a possibly larger multiverse. Think of a sheet of music paper with spots of ink scattered at random. Now imagine stretching the paper evenly in all directions. The tiny variations remain, but relative to the now larger sheet, the dots look more uniform, and their arrangement seems flatter and smoother. Inflation acted on the early universe in a similar way. It stretched space so fast and so far that any initial curvature was diluted, and any irregularities were smoothed, while microscopic variations were enlarged just enough to seed future structure. A second analogy comes from weather. The Earth's climate has patterns on different scales. There are the daily breezes, seasonal cycles, and planetary circulation. Inflation takes the small-scale fluctuations, those akin to tiny gusts, and boosts them to planetary scale patterns. Once they are large enough, gravity and pressure in the plasma of the early universe turn those patterns into sound waves. The echoes of those primordial notes become the acoustic peaks in the microwave background. The mathematics behind these analogies involves two gentle ideas. One is the cosmic no-hair principle. It says that in a universe dominated by an effective cosmological constant, like the vacuum energy of a slowly rolling inflaton, almost any initial mess fades away as space expands exponentially. Anisotropies and inhomogeneities become negligible. The second is the conversion of quantum fluctuations into classical perturbations, a process sometimes described as quantum to classical freezing. When fluctuations are stretched beyond the horizon, they can no longer oscillate. Their phases are set. Interactions with the surrounding environment and the expansion itself cause them to behave like classical random fields with well-defined statistics. The amplitude and tilt of these fluctuations reflect the inflaton's potential. Gentle slopes produce small values of the slow roll parameter that controls the rate of change of the Hubble expansion during inflation. Small slow roll values lead to a spectral index slightly less than 1, just as observed. The height of the potential controls the overall energy scale, and thus the amplitude of gravitational waves, which in turn sets the value of R. The details of reheating, the process by which the inflaton's energy converts into ordinary particles, can leave subtle imprints on the spectrum, shifting the relation between scales in the microwave background and the time when they left the horizon during inflation. As data improved, certain potentials fell out of favor. Simple models where the potential grows too steeply with the field, such as simple monomials that increase rapidly, predict too large AR with a wrong tilt. Plateau-like potentials, including the Starobinsky model and related versions that produce a very gentle roll, naturally give n_s around 0.965 and a small r, consistent with observations. There are even ideas where known fields might play the role of the inflaton, such as the Higgs field in special settings, though such models need careful tuning to fit both particle physics and cosmology. Beyond the fitting of curves, inflation suggests an extended geography of reality. In many versions, quantum fluctuations of the inflaton can keep some regions inflating even after inflation ends elsewhere. This idea is called eternal inflation. It produces a vast cosmic mosaic of pocket universes, each finishing inflation with perhaps slightly different conditions, depending on where the field landed. Our observable universe would be one such pocket, a local region with its own parameters and history. This picture is not required by inflation, but it often arises naturally in models with broad potentials. Eternal inflation opens profound questions. If there are many pockets, how do we make predictions about what we should expect to see? This is the measure problem. The answers are not settled. Some proposals weigh different regions by their volume, others by their rates of structure formation, others by more subtle cutoffs. The debate is lively, not because we enjoy ambiguity, but because the framework that gave us clear, testable signatures also invites us to consider possibilities beyond direct observation. Here, we must be careful. The strength of inflation lies in the signatures we can measure. The larger speculative landscape reminds us to be humble and to look for new anchors. One such anchor is the search for primordial gravitational waves. If we can detect the B-mode pattern from inflation, we will not only test the framework, but also measure the energy scale of inflation, a value that would reveal physics near the grand unification scale. There are also searches for isocurvature perturbations, which would indicate additional fields active during inflation, and for small departures from Gaussianity, which can distinguish among models and their interactions. Looking further, we can listen for the fingerprints of inflation in the distribution of matter over a wide range of scales. The large-scale structure of galaxies holds the memory of the initial power spectrum. The ripples known as baryon acoustic oscillations serve as standard rulers that help map the expansion history of the universe, providing additional cross-checks of geometry and content. Upcoming surveys and experiments plan to chart billions of galaxies, measure the cosmic microwave background polarization with unprecedented sensitivity, and even probe the neutral hydrogen in the early universe through 21-centimeter signals. Each of these is a new window. Together, they let us ask whether the gentle tilt remains the same everywhere, whether there are features in the spectrum that hint at events during inflation, and whether the statistics are as pristine as the simplest predictions suggest. It is also worth noting the alternatives that have been proposed. Some models aim to avoid inflation by offering different solutions to the same puzzles. Ekpyrotic and cyclic scenarios, for instance, propose a slow contracting phase before a bounce that replaces the rapid expansion with a smoothing contraction. These models attempt to generate the nearly scale-invariant spectrum of perturbations through a different mechanism. They are valuable because they keep cosmology honest. They force us to sharpen tests and to identify what truly distinguishes inflation from its competitors. As we weigh these ideas, a quiet transformation becomes clear. Before inflation, we were focused on the hot beginning and the cooling that followed. After inflation, we see that most of what we call the observable universe might be the result of a brief epoch of extraordinary expansion that took a small, uniform region and made it cosmic. We learned that the seeds of galaxies arise from quantum fluctuations, that the universe's geometry is a question that dynamics can answer, and that, for all our local complexity, we are living on a wide, smooth plain that lies on a much larger landscape. The beauty of this view is not in its drama, but in its coherence. Simple physical principles, when applied to the early universe, explain puzzling observations and make new, testable predictions. And yet, beyond the tested lies the open horizon, where questions about the inflattened's identity, the mechanism of reheating, and the architecture of the multiverse remain. We find ourselves in a moment of calm curiosity, with enough clarity to be grateful, and enough mystery to keep listening. In our last part, we will bring these threads together gently. We will look at how inflation changes our sense of time and place, how it reframes the word beginning, and how its quiet explosion informs not only science, but the way we hold the night sky when we step outside, breathe in the cool air, and feel small in a comforting way. Stand outside on a clear night and feel the scale of it. Light from distant galaxies has traveled for billions of years to touch your eyes. The glow of the microwave background crosses you with ancient warmth, a silent ocean wave that began when the universe was young. Inflation tells you that the smoothness you see is not an accident. It is the imprint of a moment when space grew so swiftly that differences diminished and a common temperature was set across what would become the observable universe. In that moment, quantum fluctuations changed their role. Usually they flicker and disappear, eternal whispers in the vacuum. During inflation, the expansion stretched them beyond return, turning private murmurs into public structure. When gravity later gathered matter into those primed regions, galaxies condensed, stars formed, and worlds assembled. The thought that every star field owes its origin to quantum chance transformed by cosmic amplification is quietly astonishing. It brings a delicate intimacy to the cosmos. The smallest laws help write the largest patterns. Inflation also softens our expectations about beginnings. We often want a clean start, a bright first moment. Inflation suggests that what matters is not a single instant, but a process, an unfolding in which a small, smooth patch becomes the arena for everything we will ever see. The phrase before inflation may refer to an even earlier time, but perhaps it is a question that loses meaning as our models run out of reach. The more helpful perspective is to learn what inflation reliably predicts and test those predictions until we are satisfied that we understand the relevant physics. In that way, science respects mystery without turning away from it. There is a subtle humility in this view. If eternal inflation is correct in any form, our observable universe may be a local patch in a larger quilt, one square among many. In such a picture, Some features might vary from patch to patch, while others are universal. It could be that the values of certain parameters, like the dark energy density, are selected from a distribution, and that we reside where structure can form. Some have used this to argue for anthropic reasoning in cosmology. Whether or not that path is satisfying, it forces us to articulate what can be tested locally and what must remain as careful, bracketed speculation. What inflation has already changed is profound and concrete. It has given us a mechanism to understand the horizon and flatness problems without fine-tuning. It has turned heavy relic worries into non-issues through dilution. It has provided a recipe for the initial conditions that lead to the spectacular web of galaxies we see today. And it has made clear predictions, from the flat geometry of space to the slight tilt and Gaussian character of the initial fluctuations that had been measured and confirmed. Perhaps most inspiring is the way inflation links human effort to cosmic history. It took decades of design, engineering, and patience to measure microwave background anisotropies and polarization. Teams of people in cold deserts and high mountains and orbital rooms tuned instruments against the quiet noise of the universe. They did so for the sake of a few microkelvins of temperature difference, small signals that carry grand stories. There is a kind of kindness in this work, a willingness to listen at the edge of hearing, to trust that nature is telling a consistent tale if we learn how to read it. Looking ahead, the story continues gently. New experiments will listen for primordial B modes and sharpen constraints on R. Surveys will map galaxies even more deeply, tracing structure with finer brushes. Radio telescopes will attempt to map neutral hydrogen across cosmic time, opening a fresh window onto the dark ages before the first stars. Together, these efforts may catch whispers of inflation's gravitational waves or reveal small features in the power spectrum that hint at events during the inflationary roll. Even a non-detection is a message, guiding us toward the right class of models and away from others. All of this feeds back into a deepening sense of place. You are part of a universe that once smoothed itself with a rapid breath, ironing out its wrinkles while leaving a fine grain of randomness. That grain is the origin of rivers of galaxies, and the reason there are places like here. The same physics that works in your lab, the quantum rules that govern electrons in a crystal or photons in a cavity, helped write the first patterns in the sky. It is as if the cosmos is one continuous fabric, woven from the same threads at every scale, humming the same song in different keys. So when you look up, you can carry inflation with you without urgency. You can picture a time when space grew unimaginably fast, not as an explosion through air, but as an expansion of the fabric itself. You can imagine the tiny ripples that became everything. And you can know that our understanding grew too, through ideas tested by careful measurement, through theories adjusted by data, through a patient dialogue between thought and sky. If this kind of calm, curiosity-driven science helps you unwind and wonder, you are welcome here. There are many more stories where this one came from. From the deep time of stars to the quiet physics of everyday materials, we explore the universe with soft voices and clear eyes. If you would like to join us for the next journey, consider subscribing. It helps this space remain warm and thoughtful, and it means we can meet again under the same wide sky.